Alrighty. Okay, well, hopefully we get a few more people joining in the next couple minutes. Um, but thanks for coming out. My name is Nick Weddock. I'm a research associate in the material science program here, as well as involved with the COSINC characterization side. And today I'll go over an introduction to X-ray diffraction, or how you put the structure in the structure property function relationships of your materials. I'd like to briefly plug the upcoming SACS workshop that we're putting on. This is primarily to introduce the new SACS instrument shown here that we have within COSINC CHR. Small angle X-ray scattering, if you're not familiar, is similar to X-ray diffraction, but your length scales are a bit larger, so we can learn things like domain size and crystalline fraction of a polymer material. If you have nanoparticles, we can get their size, shape, and any agglomeration. There are biological applications in looking at protein assembly and lipid structure. And for porous materials, we can get a measurement of the pore size distribution for both open and closed pores. This will be next Thursday, October 10th, and the QR code here will take you to the webpage with more information and a link for reservations. So for today, I'd like to go through a few different topics. First, I'll give just a basic overview of X-ray diffraction, then highlight some example measurements from COSINC with what we can do with our instruments, and then talk about some tips and tricks to improving your data quality, and then some techniques for doing quantitative analysis of lattice parameters, size and strain, and more qualitative analysis of sample textures. And then I'll go over some of the more advanced techniques we have if there's time. So with each of these sections, I'll take a quick pause to address any questions up until that point. And this technique, X-ray diffraction, has been around for quite a while. This image here is a diffraction pattern of a copper sulfate crystal that Max von Laue took in 1912. And then this here is probably one of the most famous X-ray diffraction images of DNA taken by Rosalind Franklin back in 1952. So X-ray diffraction is a very ubiquitous technique in fields ranging from archaeology to materials science, all the different engineering disciplines, pharmaceuticals, chemistry, forensics, and it can accommodate a wide variety of sample sizes, shapes, and quantities. And at least in the lab, it's more or less a non-destructive technique. The instruments are very adaptable, and you can perform measurements in a variety of sample environments, different temperatures, different atmospheres. Most importantly, we can do it here in COSINC. I'll mostly be talking today about the information you can get from outer X-ray diffraction, which will give you sort of the information you see down here, which I'll step through more deliberately as we go on. So before I go into diffraction, we need to define what we're actually diffracting from. And this is going to be from crystalline materials. A material that is a crystalline material has a long-range order that's determined by translational symmetry of kind of this smallest irreducible unit of the unit cell. I'm showing two examples of unit cells here, this being an acrylate crystal and this being silicon. And they are kind of described by the side lengths or the lattice parameters A, B, and C, and the angles between them of alpha, beta, and gamma. What we're mostly concerned about when we're doing diffraction is the planes of atoms and the different ways you can define planes within the unit cell. And these are going to be defined by the Miller indices or the HKL values. And these are going to be integer numbers that are calculated as the reciprocal of the intersection point within your first unit cell boundaries. So to give you some quick examples, if we look at our silicon unit cell here, if we draw a plane along this side of the unit cell, we can see that it will intersect our unit cell when B is equal to 1, giving us the 0, 1, 0 plane. If we tilt this and now intersect B and C at 1, we have the 0, 1, 1 family. And if we go about halfway down, and now we intercept B and C at 1/2, taking the reciprocal of that, then gives us the 0, 2, 2 plane. And you can see how 0, 2, 2 actually has 2 planes within the unit cell. If you just shift your origin over here, you'll see how this one becomes defined as well. And between the planes of each of these different families, we have an interplanar spacing, D, which is defined broadly as using the lattice parameters weighted by the Miller indices. It can be a little bit more complicated for crystals with lower symmetry, like here, but if we use a cubic crystal where A, B, and C are equal, and all of the angles are 90 degrees, our interplanar spacing D is just the lattice parameter divided by the square root of the sum of the squares of your Miller indices. So X-ray diffraction is now how we're going to learn about the crystal structure of these materials. Very briefly, when you have X-rays incident on your sample, those X-rays are going to interact with the electron cloud of the different atoms, which will briefly excite the electrons, and then as they decay back to their initial condition, initial state, they will re-radiate X-rays, and in the case of elastic scattering, which we're discussing here, the energy and wavelength of those emitted X-rays are going to be the same as the incident. So in this schematic here, in our scattering experiment, we have an X-ray source that's way off to the left here. So we can approximate that those X-rays are a plane wave. And after it interacts with the material, the X-rays are re-radiated in a spherical wave like this. Now, when we have our atoms defined in a periodic manner, what we see is that as those X-rays are re-radiated, you have nodes of constructive interference along certain angles with respect to your crystal. And this sort of coherent angle-dependent intensity is your diffraction. And the intensity and the position of this is what we're going to use to learn about our material. This is illustrating here a crystalline material, but amorphous materials with no long-range order. You will also get constructive interference at some angles, but it's going to be kind of smeared out and not these discrete values shown here. So there's a geometric relationship between the interplanar spacing in your crystal and those angles of constructive interference, and that's Bragg's law. The condition is illustrated here, and so what Bragg's law tells us is that for a given interplanar spacing D, there's an angle at which X-rays incident on your material between two planes will constructively interfere, and that's because the additional distance that the X-rays travel to the second plane is going to be equal to an integer number of wavelengths, giving us that constructive interference. And so this expression here defines that condition where our diffraction order, which is normally 1, times the wavelength is equal to 2 times the interplanar spacing times sine of the scattering angle. And the important caveat here is that your incident angle and diffracted angle are both equal to theta with respect to the lattice planes. And so what you'll do is you'll kind of rotate the X-rays around your sample to probe different planes with different interatomic spacings D. And when our wavelength is on the order of 1 angstrom, we're measuring interplanar spacings on the angstrom to kind of nanometer level in your material. In the laboratory, there are 2 primary geometries that we use for powder X-ray diffraction. On the left, we have the reflection or Bragg-Brentano geometry, where you'll rotate your X-ray and your detector at that angle theta along a goniometer circle, or you have transmission geometry where your incident X-ray is fixed at essentially 0 degrees theta, and you just rotate the detector around your sample and look at the X-rays that are diffracted. This is also the Debye-Scherrer geometry, and there are, it's common enough in laboratory XRD as well. The X-rays that we use are going to be pretty much monochromatic X-rays generated from the K-alpha transition from either copper or molybdenum sources. And we'll use filters or monochromators to remove X-ray emission lines from other less intense electronic transitions. But K-alpha radiation with these wavelengths is most common for these measurements. And our detector, state-of-the-art instruments like we have here, use an area detector to capture a larger range of scattering angle to rapidly increase the speed of data acquisition and the intensity from your measurements. These detectors can also discriminate the energy of the X-rays that are hitting the pixel. So in the case of iron or cobalt containing samples with a copper source, or yttrium, zirconium, or strontium containing samples when you have a molybdenum source, you can use that energy discrimination to remove the sort of large background you get from lower energy X-ray fluorescence from these materials. So in COSINC, we have 2 instruments to do X-ray diffraction. For the reflection mode type measurements, we have the Rigaku SmartLab 9 kilowatt. This is a very high intensity source and has optics to allow for very high resolution measurements in terms of the scattering angle. We can do measurements in ambient or a air-free or gas loading, I guess, cell. You can do some transmission measurements on this instrument, but for transmission, I'd suggest actually using the SAX instrument we have, which can also do effectively X-ray diffraction. And this instrument here is nice because now we have the capability to change temperature. We can look at colloidal samples or samples in solution. However, because it's X-ray transparent, your samples, or because it's transmission, your samples need to be X-ray transparent, which introduces a little bit more difficulty at times in sample preparation. But for kind of the rest of this webinar, I'm mostly going to be focusing on data and measurements on the Rigaku diffractometer. So are there any questions up to this point? If not, I'll move on to highlighting some example measurements so you can see the capabilities that we have here. Briefly, a powder X-ray diffraction measurement, as I kind of described before, you'll have a sample, a powder sample that contains a distribution of crystallites in sort of all possible orientations with respect to your X-ray source. And so as you rotate your source and your detector symmetrically at an angle theta, you're going to record the intensity as a function of this 2 theta angle, or the angle between the transmitted X-rays and your detector. And I'm showing here this diffraction pattern for alpha alumina powder. Now, from this diffraction pattern, there are several parameters of interest that we can use to quantify information about our sample. We're going to be looking at the peak positions, the peak intensities, peak width, and the background coming from both our sample and our sample mounting. And with some combination of each of these parameters, you can learn about a variety of different physical properties of your sample. So one thing that's been used a fair bit in COSINC is the phase identification and quantification software within the sort of SmartLab Studio 2 that's used for analysis and control of the Rigaku. The peak positions and intensity ratios that come from within your diffraction pattern are kind of unique fingerprints of each different material. And you can then use that to decide what materials might be in your unknown sample. So in this case, I'm showing you an example from a corroded steel pipe. And what we do with the software is once we take our diffraction pattern shown here in red, you'll fit peak positions and peak areas, and then match those within a database of known crystal structures. And you can refine that by saying, okay, it should have only these elements to narrow down the breadth of the search. And what you'll get is a result like this, where you can see several candidate phases and their expected peak positions and intensity ratios as compared to your diffraction pattern. And once you go through and select, your candidate phases, in this case, the calcite, phosphite, and goethite, in addition to the carbon steel, you can, based on the intensity ratios, estimate the weight fraction of each of these phases. And so for this sample here, we have a table of the estimated weight fraction. Lime was not included in this calculation because you can see that where the strong peaks are expected, we don't really have any diffraction. So there's no real contribution from the calcium oxide. One thing that I will caution in this case is that the accuracy of your weight percent calculation really depends on how you prepared your sample. And I'll touch on that later. Another thing we can get is the lattice parameter and any lattice parameter changes for a sample that's been alloyed, a battery material that has partial intercalation. In either of these cases, you expect a shift in lattice parameter compared to the parent compound. And so here on the left, I've measured a lanthanum nickel 5 based metal hydride alloy, or AB5. And we can see that the calculated lattice parameters in green for the parent lanthanum nickel 5 are pretty far off from what we actually observed in X-ray diffraction. However, if I go ahead and tweak the lattice parameters just a little bit, less than 2%, you can see that our peaks line up pretty well. And so this points to the power of X-ray diffraction and how sensitive it is to really subtle changes in interplanar spacings, giving you very high accuracy at determining lattice parameter in your materials. We can also look at crystallite size. If your crystallites in your material are less than 100 nanometers or so, there will be an observable broadening of the peak widths as a function of the crystallite size. And so this here is the Scherrer equation, which relates the crystallite size to the width of the peak times cosine of your diffraction angle. K is a shape constant depending on the approximate shape of each crystallite. But what we see here is that if you have a broader peak, that tells us that we have smaller crystallites. This will give you a single value, but you can also get a distribution of crystallite sizes in terms of volume percent by doing a more careful analysis. An example of this is over here on the left, where we had a metal oxide film grown with increasing dopant concentration as you move down. And we can see that for the high dopant levels, we have very broad peaks corresponding to about 5 nanometer crystallite size. But for the samples with less dopants, crystallite size increases to about 20 nanometers. So any questions on sort of those example measurements?
Okay, I want to ask you, is phase identification automatic? Or you have to provide some information?
You can, for the phase ID, search the entire database of crystal structures that we have, but there are tens of thousands. And so if you have an idea of what your constituent elements are, you can input that and that'll really narrow down the search. Otherwise you could get some really strange compounds, uranium phosphides or something is one that I've seen show up just on a broad search.
Okay, but this XLD does not provide any elementary information, so you have to know the sample, kind of, to identify the phase properly.
Right. And some crystal structures can be distinct enough that it
Uh-huh.
will recognize a specific material.
Uh-huh.
For that example I showed, I wasn't aware that calcium could be in there, but when I did a
Mm-hmm.
broad search, it came up with calcite. And the person who provided the sample said, yes, that's probably in there. So it sometimes can get it right, but it's not 100%.
Okay, thank you.
Okay, so now I want to talk about sort of how to optimize your sample to get the most accurate peak positions, peak intensities for the best quantitative analysis of your sample. An ideal sample for X-ray diffraction would be thick enough or large enough that you have a constant illumination volume of your X-rays. So in reflection geometry, if you have heavy elements in a very thick sample, you're going to have a constant area of illumination as you scan theta. If you have a sample that has light elements, using a transmission geometry will, in a capillary type measurement, ensure that as you scan your detector angle, it's still sampling from the same volume of your material. You want a completely random crystallite orientation, and you can do that for a powder by kind of lightly packing the sample as to not introduce texturing, and additionally rotating or sort of oscillating your sample to avoid any preferred orientation effects of the powder. And if you have a bulk or bulky sample, you'll want to pulverize it into a fine powder. Now your powder the particle size should be on the order of 500 nanometers to 1.5 microns, and that will ensure that the X-rays completely penetrate each individual particle. And this will give you the texture kind of like flour is what you're aiming for. And you also want a very narrow size distribution if you're less than that 500 nanometers, so that you don't have any broadening from the size. When you go to make your powder sample, if you're pulverizing a larger sample, be cognizant of the fact that as you grind it, you might introduce some defects that will give you broadening of your peaks. So you might consider filing or some other more gentle technique to obtain the powder, and annealing your sample after it's been pulverized. So if you're able to meet all of these criteria, then you'll have a data set that's really optimal for a full quantitative analysis. And as you relax them, depending on which one you're not quite meeting, the accuracy of different parameters will decrease. Now, obviously, you're not going to be able to make this ideal powder all the time. So that's fine. It's just important that you, based on your sample geometry, understand what limitations you will have in your analysis. So here I'm showing kind of different common sample geometries and sample states, and what parameters of the measurement you can trust will be pretty accurate or maybe not so much. So for bulky samples, peak positions can generally be pretty reliable, but the peak intensities and their ratios and then the peak widths can be affected by the sample geometry. If you have a sample that was prepared and you didn't remove all the solvent, or you had some dealloying, your peak positions will be suspect. A textured film will give you, peak intensity ratios that aren't optimal. And kind of moving on through here, you just need to keep in mind that not every sample is perfect. And if you have a geometry that you're not familiar with, feel free to ask me and we can discuss, maybe the best way to prepare it, or what limitations you have in the analysis. So even if we have a non-ideal sample, we can still minimize our uncertainties by not just preparation, but also mounting the sample and aligning it appropriately. So on the Rigaku instrument, we have several different measurement packages That will allow you to configure the optics and the samples to give you the best data quality that you can. The Bragg-Brentano or BB package is your standard powder XRD. If you have a uniform packed powder like the alumina here, you'll use BB mode. Thick films are also BB, and that'll give you really great data quality for phase ID, lattice parameters, size, and strain. If you have a sample that's not so nice and it's kind of rough, like this powder here, you'll need to collimate and use a parallel beam to eliminate sort of that varying height effects. And if you have a thin film, so here we have 50 nanometers of gold on silicon, a BB or any type of symmetric theta 2 theta scan is not great, because as you get to those high angles, your X-rays are just going to penetrate through the film and minimize diffraction. So you'll actually do an asymmetric scan where you set your X-ray incident angle to be very small, and that will increase the effective volume of the thin film that you're sampling because you don't have deep penetration. And then you're just going to scan your detector 2 theta angle. This is assuming that your thin film here has some degree of powder crystallinity, that you will have crystallites that are oriented in more or less all possible angles to allow you to collect the whole diffraction pattern. So if you have a powder sample or a sample that you can pulverize, in order to enhance and improve your data quality, as I mentioned, grinding it to a small size, we have mortar and pestle that you can use. Just, if you're really grinding on it, you can introduce defects. If you have flaky powders or a sample that has some preferred texturing or fibery powders, if you can't grind those, what I suggest is placing the powder on the edge of your sample holder and just dragging a glass slide across and don't press down, and this will help to average out to some degree the orientation effects of your powder. If you have a sample that's been deposited as a film, if you can scrape that off and try and pulverize it, that'll help with any preferred orientation. And finally, you can use the phi attachment base to rotate the sample sort of about this vertical direction. And I'm working on currently a capillary rotation stage that will rotate in the about the axis perpendicular to this to really help with those orientation effects. For powder samples, we have a variety of ways to mount your powder. The glass powder holder is probably the easiest in terms of alignment. We also have some silicon wafers with little notches etched in that will give you a zero background contribution. In any case, if you don't have enough powder to completely fill the channels, it's more important to center that pile of powder and then lightly press with a glass slide to make sure that the top of your powder is flat and flush with the edges of your sample holders. This glass holder will be used with a different attachment head that's shown here, but the zero background stage can be mounted on our 4-inch wafer sample plate or our narrow wafer plate here. Or you can load powders into an air-free holder, which has inserts for powders. It's got thin films as well as zero background capabilities. I will note in the Gaku software, this narrow wafer plate isn't an option, but if you want to use this, when you're doing your alignment, just select the 4-inch wafer sample plate, and the height of this is equivalent to the 4-inch wafer plate and the 0 to 3 millimeter spacer. If you have bulky samples that you can't pulverize or would be difficult to pulverize, you'll want to mount them so that you can get the flattest surface possible facing up. So this mineral here, if I put it on flat side down, you can see there's a rounded surface. So what I did was used a little bit of the crystallographer's clay with the instrument to rotate the sample and give that flat surface facing up. And if you have, say, porous material decorated with nanoparticles, if you can, it might be good to try and compress it or crush it to eliminate any variable height effects and effectively increase the amount of sample in the volume. There are the grazing incidence package and phi rotation stage that I mentioned are not standard packages in the Rigaku software. We can see that BB and PB are, but if you want to use these techniques, you can import the custom packages that I built to your own profile. So when you're logged in your profile, and you go to the activities panel, if you look at the package activities and select this import button here, we'll open up the import window and you'll select the administrator user to import from. And you can bring in the GIXRD, 0D mode package, the BB with phi rock, that's that rotation. And then once it's complete, the capillary spinner stage will also be there. Select the ones you want, click OK, and now you can see that it's been added to your profile for use whenever you have samples that would benefit from that. So once we've prepared our sample to be sort of the best state that we can, we also need to properly align the sample. We want to put the sort of top of the sample or wherever you're going to be primarily diffracting from at the center of that goniometer circle that your source and detector will rotate around. If you have the powder sample in the glass slide, you'll use this height reference sample plate, and due to the optics procedures, the top of this plate is going to be at the center of your goniometer circle, so you don't need to do any height alignment. But this is why I stress that you want to make sure that your powder is flat and flush with the top of that sample holder, because that's what you're going to be aligning to. For bulky samples that don't quite have that flat surface or a approximately flat surface, you'll want to use the curved sample or Z-scan only option. And you'll use the 4-inch wafer plate or the narrow wafer plate for this. And there are a couple parameters that you need to input before you do the alignment. You need to input the sample thickness and the sample height. If you hover over this little eye here in the software, it'll bring up this diagram of how the software defines the geometry of your sample, where it's a bit counterintuitive to me, but the height is the distance across the beam. So knowing both the height and the thickness is important to have the best alignment. Thickness, you want to be approximately 0.5 to 0.7 millimeters accurate. If you're doing a powder in the zero background stage, you can get away with just doing the curved sample alignment for this, and it will be 1 millimeter thick. For a thin film, though, you need to align both the height and flatten the sample with respect to the X-ray beam. And so you'll use the flat sample alignment procedure, again, making sure to put in a height and thickness that's as close to correct as you can get. And it will, as part of the alignment, you can get the exact thickness if you need. So now we've got our sample aligned. There are a few considerations when you're doing your measurements that will help to improve your data quality and ensure things like constant illumination volume, etc. And particularly with small samples measured at low angles, one important consideration is the beam footprint, or the size of the beam on your sample as a function of your detector angle theta. And you can see that at low angles, because of the geometry of the beam, you really spread out the size of the beam on your sample. And you want to avoid spillover whenever you can, because that means you're no longer in that constant illumination volume. You have X-rays extending off the sides of your sample, both in the width direction and the height direction are important. the width you will select in BB mode and PB mode by changing the size of your incident slit. In BB mode, this is given as an angle, which is the divergence angle of this cone here. And I've plotted up here the footprint size in millimeters at differing 2 theta angles as a function of that incident slit angle. That outer stage is roughly 25 millimeters in height. And so we can see that for the default half-degree incident slit angle, any measurement below 12 degrees 2 theta is going to have some beam spilling over onto the sides of the sample holder. And so this is important to consider, particularly when you have smaller samples. You might want to refer to this chart, and you can change the incident slit angle in your measurement just by changing the value in this box here. In PB mode, incident slit will be given as millimeters, and it's a kind of more simple geometric construction to take a completely collimated rectangular beam and calculate the beam footprint. The making sure you don't spill over on either side and the height will be based on your length limiting slit selection. So this is why in alignment procedures, you want to make sure the height is correct, because the software will update and tell you to change the length limiting slit if necessary. So save that for the alignment step. Don't change the length limiting slit in your optics alignment step. Wait till the sample. You can also get rid of the effects of your beam footprint if you use a 0D measurement instead of 1D measurement, because the horizontal slits that you install will reduce and eliminate effectively the vertical divergence of your diffracted beam. But this is going to cut down a lot on your intensity, so it may not be preferred for your measurement. Another important consideration for peak width analysis is the size of your data binning. In the measurement panels, your step size here is going to be the width of the bins of your intensity versus 2 theta histogram. In general, there's a couple considerations and that you want to do a proper line width analysis. You're going to want at least 5 data points above the full width at half maximum of your peak to get a more accurate peak shape determination, Gaussian or Lorentzian. And you want to make sure that your data collection range extends well into the tails of the peak. So this figure here on the right is showing a Lorentzian function that's being truncated at a decreasing number of widths of the peak, so decreasing number of sigma effectively. And you can see that below 15, you're really starting to truncate the tails, which will make analysis of both determination of Lorentzian versus Gaussian difficult, as well as just having a poorer fit because you're losing a lot of the information out here. Generally, in a BB mode measurement, our step size is 0.01 degrees. That's usually reasonable for standard, maybe less than perfect samples. But if you have a very crystalline, perfect sample that has very narrow peaks, you should probably consider reducing this to some smaller amount to make sure that you have enough data within or to define your peak. For grazing incidence measurements, I mentioned you're going to have a shallow incidence angle. So in the GI-XRD 0D mode, you have to change a couple parameters. First, you'll want to make sure that your scan mode is now the 0D type measurement, because that's going to eliminate our footprint effects. You're only going to be scanning the 2 theta axis, so this should be selected by default. And then you're going to pick your incidence angle, generally between 0.2 to 4 degrees, to change, there's optimization between peak breadth and penetration, going from narrower peak breadths at 4 degrees, but higher penetration down to the opposite. And you want a very flat sample for this because you'll need to set your incidence angle and make sure you're not kind of just hitting different parts of your sample. You want to capture the full illumination. To set the incidence angle, you're going to go into the Set button under Options. You'll make sure that the first row is selected and the axis you are setting is omega, changing the origin to the incidence angle you would like. In this case, it's 0.45 degrees. A bit more information and some tricks for maximizing your intensity in a grazing incidence measurement. Every material that you're going to measure has a index of refraction for X-rays, where it's given by a wavelength-dependent dispersion and absorption factor. These values are tabulated elsewhere and can be looked up online. This is one of the websites that I like to use. And you're going to, the energy that you are looking for copper sources is going to be 8,047 EV. And from this index of refraction, you can calculate the critical angle for total external reflection. So the angle at which X-rays will no longer bounce or reflect off your sample, but they'll start to penetrate inside. And that's visualized in this plot here, where I'm calculating the attenuation length or penetration depth effectively of X-rays into nickel oxide as a function of that incidence angle. And around 0.3, 0.35 degrees, you see that this attenuation length jumps up very high, telling us that we've now entered the region when we are penetrating into the sample. And this sort of region, transition region here, has some interesting physics that you can utilize to enhance the intensity from your sample, assuming that it's a nice flat sample. If you set your incidence angle to be kind of just below the critical angle of a substrate with the film on top, you'll generate some evanescent standing wave at the substrate and film interface that will enhance the diffraction signal from that film. And this is useful if you have a very thin film, 10 nanometers or less, because that's about the penetration depth of that standing wave. If you go slightly above the critical angle, so you're just penetrating the material, it's just like a fiber optic cable. You'll get total internal reflection, again, enhancing the signal of your diffraction. And so that's illustrated here, where we're looking at the intensity of the 002 Bragg peak in a metal halide perovskite nanocrystal thin film. And you can see that the intensity increases and maximizes more or less around the critical angle for that material. But this is, again, the caveat that you need a very flat sample for this. So any questions at this point?
Okay. So when do you want to use grazing incident measurement?
There's not like a fixed cutoff in terms of height, because it depends on the elements in your sample.
Mm-hmm.
I would say, if you have heavy elements, 100 nanometers or less, if 50 nanometers or less, you have lighter elements like alumina, you might want to use grazing incidence even at 2 to 4 or 500 nanometers. It's generally, if you don't know, it's pretty quick to just do a BB measurement of your material. And if you don't see anything, then maybe you want to go to grazing incidence, because that'll take it a little longer to set up and a little longer to measure.
Okay, if I have a very thin film, like up to 10 nanometers,
Mm-hmm.
then what would you do to identify the phase?
So you'll get basically a similar diffraction pattern, unless there's heavy texturing. But if it is crystalline, you should see diffraction peaks. And you can do the analysis just like you would for a powder sample.
Okay, so you would start with a standard BB? That's your...
If you know it's 10 nanometers, I wouldn't start with BB, unless it's like 10 nanometers of uranium or something.
Okay.
But even then, I might, yeah.
So 10 nanometers of, say, aluminum, then you don't do the BB.
I would just start with the grazing incidence. I wouldn't do BB for 10
Okay.
nanometers.
So the grazing incident measurements are more for very thin, flat, so something like thin film on the substrate, flat substrate will be useful.
Yeah, that's correct.
Okay, thank you.
Okay. Seeing I'm maybe going a little slower than I wanted, so I'll try and step through some of this a little quicker just to get to the end. But now we've had our measurement configured, and now we want to measurement configured well, and now we want to actually start to quantify the results from our data. And so, first thing that most people are interested in is lattice parameter quantification. And so I'm going to go through the considerations that you have when trying to do that measurement. The primary thing that you want to consider when doing a lattice parameter measurement is if your peak positions are actually in the right spot. There are several things that contribute to errors in that measured peak position. The primary one being sample displacement. And we consider displacement in the vertical direction as well as the horizontal direction away from that center of this goniometer circle here. Basically, if you have sample displacement, your ideal diffraction pattern here in blue with the peaks matching the expected positions will shift one way or the other based on the magnitude and direction of your displacement. So you can see that if your sample is higher than it should be, you're going to measure angles that are higher than they should be, and that will give you a smaller lattice parameter. And the reverse for samples that are too low. And this is this kind of basanite mineral diffraction pattern here. But just through geometry, you can figure out what this delta theta would be. So in the vertical case, it's going to be displacement times cosine theta over r. And then if you add in the horizontal component, you have this d sine theta, where here d is the horizontal displacement, not the interplanar spacing. And the apparent shift in your lattice parameter, or your delta dm over dm, will be given by this expression here. These expressions here are applicable for the Rigaku when you're doing a 0D or 1D scan and rotating the detector around this goniometer circle. If you're doing a transmission measurement on the Xenox, the vertical offset is not really a problem because you just shift your pattern on the detector, but horizontal offset from the 0 position and a incorrect sample detector distance will really affect the measured position, and that will give you this expression here, just pointing out that a displacement on a flat plate detector or a detector rotating around the goniometer circle are going to be different. If you have an error, if you take your measurement and you know what lattice parameter you should have, and you see that you're not matching those values, you might also have a lattice parameter that's not what you expect, and that will shift your peaks in a way that's different than the displacement. So we can see here the functional form of the lattice parameter shift is different than your displacement. You can work this out just by differentiating Bragg's law, and you get that the shift in peak position is going to have a tangent dependence on the angle. And so in this case, this delta D is the offset of your interplanar spacing given by a change in lattice parameter. So here, this is a constant. So if you kind of just maybe plot out the angular dependence of the shift you would expect, this can give you an idea of what's contributing to your error. But there are more convenient ways to deal with this. The Nelson-Riley method for displacement correction is very common. So if we go back to that expression that we derived previously, what you'll see is that if you want to minimize any errors in your lattice parameter measurement, it's best to go to very high angles, and your error would go to 0 in the completely backscattering of 2 theta equals 180 degrees. Obviously, you can't measure at this angle, but what this is telling us is that if you can measure diffractions out to higher and higher 2 theta values, those are going to be closer to your accurate lattice parameter value. And I showed that expression before of the shift in lattice parameter as a function of your sample displacement. And so if we take this expression and we just plot the lattice parameter for each Bragg reflection as a function of cosine squared theta over sine theta, a linear fit of that plot should remove any of the displacement errors, and at the 0 intercept will be your true lattice parameter value. Now, Nelson and Riley did some additional empirical analysis, and they added this cosine squared theta over theta term that can help to account for any absorption correction. And generally, this improves the accuracy of the lattice parameters you get from this type of analysis. This is great for cubic systems, and it becomes a little more difficult when your lattice parameters are not equal and you have a coupled system of equations to deal with. Really quick, if you're doing brazing incidence measurements and trying to get the lattice parameter, you need to account for the refraction shift of the incident beam. Because our index of refraction is greater than 1, your incident beam will be deflected to a smaller angle than your initial intention. And because of that, the diffraction angle you measure is going to be greater than the actual Bragg angle. And the difference, this delta 2 theta, is given by this expression here, where phi is our incidence angle and delta and beta are the parameters from our index of refraction. And so this just gives you a linear offset in your 2 theta values. And so if you calculate this based on your incidence angle, you can just subtract that and correct your data. And I bring this up because if you plot this out for your known materials, then your shift in the peak position is largest at the critical angle. So I'm showing here the reference. This was an iron oxide, and then I've calculated it for nickel oxide, and they're pretty similar at copper energies, but we see how much you can have an offset. Okay, size and strain. Your strain broadening, we can go back and look at this expression here, but now we're saying that delta D is not a constant. Now you have a variety of lattice parameters throughout your sample due to inhomogeneous strains, at the regions of compressive strain, tensile. What this will do is not shift your peak, but just broaden it. And typically strain broadening gives you a Gaussian shape, which is indicated here. And size broadening, when we used the Scherer formula before, but if you go through some of the math, you're often approximating size broadening as a Lorentzian line shape, but this is really only if you have a normal distribution of different sizes of your crystallites. When you go to determine whether you have size or strain broadening, experimental intuition can be really helpful in narrowing down the source of it. So if you consider how your sample was made, what the crystal structure is, that's really key to getting that first step in your analysis. So on the right, I'm showing here X-ray diffraction of nickel hydroxide, or the beta phase, where your crystal structure is actually sheets of these nickel hydroxide layers with the direction normal to those being the C direction of your unit cell. And if I look at my diffraction pattern and I index each peak, I can see that the 00L family of planes are much broader than the H00 or mixed indice peaks. And so what that's telling me is that there's just disorder in that interlayer stacking only. And this is likely coming from some solvent intercalation or water that's existing between the planes and giving you that inhomogeneous distribution of lattice parameters. So this would be primarily a strain effect that I'd want to refine for. On the left, I'm showing you here a in situ measurement of hydrogen uptake by palladium particles that were produced through gas atomization. You might expect that pulling in hydrogen will give you some strain effects, but the peak breadth doesn't really change very much through the experiment. It's always kind of broad. So that's telling me that the predominant contribution here is actually a size effect. They must be very small particles. And indeed, some TEM measurements confirmed that they were 7.5 nanometer crystallites. Now, before you go ahead and just look at your peak shape and take the width and get your values, you need to consider that there are inherent broadening coming from the instrument itself, basically by selection of the Solar slits, the beam size, the beam profile, and the energy resolution. So when I mention energy resolution, that K alpha transition, there's actually two that are very close in energy, and we don't have a monochromator good enough to select between one or the other. And so this will introduce a broadening because you actually have diffraction at two different wavelengths. This broadening is very small at smaller 2 theta angles, but as you get to larger 2 theta angles, you'll see that your Bragg peaks start to split. And if that splitting is more or less half the intensity of the primary peak, that's just your K alpha splitting. This is not a secondary peak that's showing up. And most software know how to correct this, so it's not a huge worry if you're using a specific refinement software. I will say if you see this splitting below like 40 degrees, you're going to want to probably reduce that step size if you want to do any peak width analysis. And this instrument resolution will be involved with the broadening from your sample and kind of, again, complicate that peak shape analysis. But luckily, we can just measure the resolution function of our instrument. I use a NIST standard reference of lanthanum hexaboride and basically calculate as a function of theta the broadening from our instrument. And I can, if you use, depending on the refinement software you use, just ask me for the file. I can give it to you. And if you're using a non-standard configuration, you'll want to make sure to measure the broadening function yourself because it will change. Finally, and I think this is probably an all right slide to stop on, if you want to decouple any size and strain effects, there are semi-quantitative methods to do this. For size and strain broadening, we'll use the Williamson-Hall method, which assumes that the breadth of your peak is just the sum of broadening from size effects and strain effects. And if we take the expressions for the size or strain broadening and size broadening, we find that you can make this relation here, where the breadth times cosine theta is equal to your strain times sine theta plus some constant as a function of crystallite size. And so by plotting this, the cosine theta versus sine theta, a linear fit, the slope will give you your strain weighted by some constant, and the intercept, your size, again weighted by this shape factor. And in this analysis, it's important that you remove the contribution from your instrument when looking at the breadths that you plug into this equation here. Looks like I'm at time, so I guess I'll go ahead and stop. Are there any questions before everyone heads out?
Okay, no questions. I'm going to stop recording here.